Along the hook of Scorpius is a bright red star. It's called Antares, and it's a red supergiant star. So this is a very large star, much larger than the sun. If we put Antares where the sun is, it would stretch out well past the orbit of Mars, over 700 times wider than the sun. It's about 550 light years away, and that's actually relatively close, at least compared to the size of our galaxy. And its large size for a star and its relative closeness makes Antares one of only a few stars that we have taken photos where we can see the surface, where we can look at the atmosphere of the star. Most stars, if you look at them even through a telescope, they'll only look like a small dot of light. Let's look at some of the photos that were taken of Antares. We're going to be bringing up a picture that's taken by two different sets of telescopes, and this is in radio waves. So radio waves are going to be longer wavelength type of light, basically a lower energy light than what we usually see with our eyes. And so the little inset here on the left side, that's taken by the ALMA telescopes, where you're seeing the star itself, Antares, the surface and some of the lower atmosphere. And then on the right side, we're seeing a view taken by the VLA telescopes, which is a much wider view, and it's showing us on the right side stellar winds that are blowing off of this star, and they're actually getting lit up by another star, a small companion of Antares. And it's from this type of real data that we can construct a cross-section, basically scientists piecing together what the layers are in the atmosphere going away from this star, from its surface. So we're going to take a look next at a cross-section that shows us basically an artist's view based on this real data of what Antares looks like, what the layers are. So here we see the artist's depiction of the layers of Antares. The innermost ring is what we think of as the surface of the star. That's the photosphere. And you can see down at the bottom of the chart here a comparison to distances in our solar system. If you put Antares where the sun is, just that surface is extending past the orbit of Mars. And above it are the layers of the atmosphere that we can tell from the data, the radio telescope data. And so we're seeing the layers of the atmosphere, the lower chromosphere, the upper chromosphere, and where those stellar winds are flying out. And just the atmosphere of the star extends out almost to the orbit of Saturn in our solar system. The stellar winds go out far beyond that. We think about 12 times the width of the star Antares. And from this radio data, we can also measure the temperatures of the gas in each region. And normally for a star, when you come off the surface of it, the temperature is going to start to drop, but then in the upper chromosphere, it often gets hotter. In our own sun, this jumps up quite a bit. It can go up to 36,000 degrees Fahrenheit. Whereas here, this star is a cooler star than our sun. All red supergiants are going to be cooler than our yellow sun. But we actually found surprisingly quite cool upper chromosphere, around 6,300 degrees Fahrenheit. So a lot cooler than our sun's chromosphere. And this was a bit of a surprise too, because we've looked at this star in visible light, in UV light, and seen hotter temperatures there. But most likely, those pictures in visible and UV are showing us smaller pockets of gas that might be hotter. There's going to be a lot of material bursting off this star, and so the atmosphere might not be perfectly uniform. The radio waves here are going to show us more of the gas, more of the temperature that the overall region has. So we're going to actually take a look at what it would be like to be close up to a red supergiant star, an artist's depiction of actually flying by a star like Antares. So this artist depiction that we're seeing is actually based off another supergiant star, Betelgeuse, but it's still a similar type of star to Antares. We're seeing stellar winds that we're flying through now that are shooting far off the star, just like we saw for Antares. But as we get closer, we start to see large bubbles on the surface of the star. That's actually convective zones, huge areas where material is turning over in the star, getting dredged up from deeper in the star. And that's helping drive the stellar winds as well. And those stellar winds are sending material back out into space, and even freshly fused elements made in the star. Our next object is low on the horizon between east and south, but incredibly bright. It's not a star, but a planet. The planet Jupiter, the king planet, the biggest planet in the solar system. And it'll start rising after sunset towards the east there. It won't always be in that spot though. The planets move around in the sky. We find them in different places from month to month and year to year. The planets are all going around the sun just like we do. So we see them move around in the sky compared to the much more distant background of stars. We're going to take a closer look at Jupiter by flying out to it through space here in the planetarium. It'll get dark for a moment, and you can think of that as us getting into our spaceship for our flight out to Jupiter. We're on the Earth still, but now we're going to lift off of Earth and fly out to Jupiter, traveling hundreds of millions of miles through space. As we get closer, we'll start to see 4 of Jupiter's largest moons. These are the Galilean moons. You can actually see them through a pair of binoculars or a small telescope. So now we have a much closer up view of Jupiter, the biggest planet in our solar system. Now Jupiter is a gas giant planet, and it's mostly made of hydrogen and helium gas. But there are trace amounts of other molecules, things like ammonia and water vapor, and that's helping give us the colored bands that we see across Jupiter, especially as these different materials interact with sunlight in different layers. We're actually studying Jupiter and its internal layers and structure right now with a spacecraft. NASA sent it. It got to Jupiter in 2016, and it's called Juno. It's been mapping the extensive magnetic fields around Jupiter, trying to understand more about the interior of this planet. One of the most important measurements that Juno is making is to look at the water content in the clouds of Jupiter. Water is not just important for life, it can also tell us about where a planet formed in the solar system when all the planets were being born. Jupiter is actually the largest planet and possibly the first to form. It contains most of the gas and dust that didn't go into the sun. So the sun has most of the material from our primordial cloud, but Jupiter has the next most. And so knowing how much water is in Jupiter can help us determine how Jupiter formed, where it formed. It tells us a lot about how warm or cold Jupiter was when it formed. And so it can narrow down the scenarios for how our solar system was born. In 1995, we got a measurement of the water content from a spacecraft called Galileo. It ended its mission by diving into Jupiter, and so we measured the water content by going into the planet. They measured it at about 75 miles. But what they found was that there was a lot less water than what we see in the sun. This was very unexpected. If it's true, it would mean we need completely new models for how our solar system formed. But we have other models that assume a higher content of water that make more sense to us. These are models that how much more water Jupiter has in the sun can tell us exactly how and where Jupiter formed, and tell us a lot about the other planets and how they formed as well. So we wanted to take more measurements of the water content at Jupiter, and we've done that with Juno. Juno can look at larger areas of Jupiter with an instrument that measures microwaves that are reflected off of the clouds. It tells us the water content in those clouds, and it can even do so at deep levels. And about 93 miles deep is where we've gotten some measurements already, and they're showing 3 times the water content that's in the sun. So much different measurement than what Galileo found. These are wider areas and probably more reliable measurements. Galileo was most likely unlucky. It fell through a dry patch on Jupiter, and Juno is collecting measurements that can tell us in detail about the water content even across the planet. As we collect more and more observations, we may know how much water is in Jupiter at different latitudes as well. And that sort of detailed mapping will help us figure out how our solar system was born. We're going to end with a video. It's a compilation of pictures from the Juno spacecraft that essentially allows us to fly with Juno on its orbit around Jupiter. We're going to start near the equator of Jupiter and swing out towards its south pole. Juno's on a polar orbit, so it goes over the north and south poles of Jupiter and gives us a view that we don't get from the Earth. Now, it starts in close, a few thousand miles above the cloud tops, but then Juno swings out to over 5 million miles away from Jupiter. And the reason for that is so that they can map the extensive magnetic fields around Jupiter. Those magnetic fields are generated inside of Jupiter, so studying them, mapping them in detail, tells us about the internal structure of Jupiter. And what we found so far is that the outer layer of Jupiter, where the storms are, the cloud tops, that extends much further into the planet than we once thought. It goes 1,900 miles into Jupiter, and that's still only 4% of the way into this giant planet.